I was just wondering, what is the biggest thing that you enjoy about Ram Rocketry compared to other things that you've done at CSU?
So the things I've enjoyed the most about Ram Rocketry is the camaraderie between everybody. That can include students that are not necessarily in the aerospace engineering degree path.
What is the biggest thing that you worry about on a launch day that could potentially go wrong for not just the rocket itself and the team?
I'd come back on Tuesday and take them. Actually, I come back tomorrow and take them.
One of the bigger issues that could happen is the rocket just not launching in general, like a battery switch doesn't work, or we have some issues with the physical rocket itself, whether it be a nose cone is tilted off to the side, it might be a fin or a wing that has been dinged, therefore it's going to throw off the trajectory of the rocket. Another big thing that could go wrong would be a rocket shooting up and then completely going astray. Hitting a car, God forbid, hitting a person, or just flat out losing the rocket altogether.
What's the first thing that comes to your mind when something like that happens?
The first thing that comes to my mind when something like that happens is head down, and I hope everyone's okay, because I have personally not seen that, knock on wood, and I hope I never get to see that.
Yeah, so here at Ram Rocketry, I initially was the internal config guy for the AFS rocket. Since I've moved to more of a mentor role and making sure people are taking care of their rockets and doing the right thing. Yeah, well, rocket science is just the science of rockets, right? It's understanding how a rocket moves throughout the air, moves throughout vacuum, just different medium, and how we can utilize that information. Yeah, so Tarkovsky's rocket equation is the change in velocity is equal to the exhaust velocity times the log of the mass ratios. The exhaust velocity also equals the specific impulse times the gravitational constant, which is just the acceleration of gravity from the Earth specifically. It varies depending on the different celestial body you work with. So Mars would have a different acceleration of gravity compared to Earth. Yeah, the escape velocity for Earth, well, the escape velocity one is very different from, let's say, the velocity to achieve orbit. I think if I remember correctly, the escape velocity for Earth, 43,000 kilometers an hour, 43 kilometers a second. And that's what to do is that's to escape the gravitational pull of the Earth. So if you don't achieve that velocity, that orbiting body would eventually come back towards Earth. Rockets are a very unique case because how we're doing it is you have the rocket body filled with the propellant and you use very extenuous finite element analysis and fluid dynamics to get an understanding of the nozzle and how we can utilize the best velocity to have it leave the rocket nozzle. We're essentially turning chemical energy into mechanical work from the propellant to get that rocket to move forward.
My name is Jay, as you know, and I'm the president here at Ram Rocketry. I overlook all the projects that we do, and AFS in particular is Active Fin Stabilization. It is a rocket that is supposed to have two sets of fin. One is dynamic, which is movable, and then the other one's static. The purpose of this entire flight is to give the rocket a on-demand trajectory and realize the kind of errors it's making and then iterate over a few months, a few years even, and get that error as down as we can, and then have it hit a particular set of GPS coordinates. In terms of Ram Rocketry, I am in charge of overseeing the three projects that we do. Active Fin Stabilization, or AFS, is one of those projects. A 3D simulation involves putting a virtual object in an enclosed space and simulating the flow of air, whether it's laminar or turbulent, along the central axis of your vehicle, in this case, which is a rocket. And so what you would do is you would have an inlet, which is kind of like the source of your air that is passing through the rocket when it's hitting those active control surfaces, in this case, which are like the fins. You kind of just want to analyze what the air is doing around them when you have fins at different angles, so that you can determine what is the air deflection, what is the fin deflection you want to be, what is the threshold of the fin deflection before you have air pockets kind of just vortexing off instead of actually being deflected. I think in this case we have about 20 degrees of fin deflection, which is anything above that is just destabilizing the rocket instead of guiding it to a certain point. Ideally, we would want it to go plus or minus 5 to 10 degrees, and that's what we have right now. Necessarily for active fin stabilization, we want it to be a rocket that people can take inspiration from, that people can use to demonstrate how you would go about designing a full system backed by simulations.
My name is Ian Leary. I am a mechanical engineering student here at CSU, and I am the project manager of RAM Rocketry. So I am the team lead of Active Fin Stabilization. This is a rocket that has 4 fins at the top of the rocket that can rotate on their own servo motors and basically control and correct its trajectory on the way up. This is the second iteration of the project. We were working on a version last year that went really well for one flight, but the parachute failed to come out and it plummeted into the ground at about 120 miles an hour. This second iteration, we've corrected a lot, made a lot of upgrades, and it's going to go a lot better.
So everything there is done. It cannot be changed.
I'm Selin Ertopuz. I am the vice president of the club. I oversee the people, the meetings, and the projects. I mean, to me, rocket science is just having fun and building rockets. I've learned a lot and gained a lot of hands-on rocketry experience that I usually do not in my classes. I've gotten to build more rockets, manufacture more things, get more experience, and meet more people that enjoy rocketry like me. In the AFS project, I mainly have worked on the design, the building, and the general working of the rocket structure. So that includes how the recovery system works, how the rocket is built, where we integrate the camera, where the screws go.
It's been great. I mean, I joined my freshman year. I kind of did it to meet a lot of people because, you know, as a freshman at college, you don't really know anybody. So I thought, oh, I really like rockets. You know, meet some similar-minded people, and then we can, you know, work on rockets. And yeah, I think it's a great group of people over there that, you know, I've gotten closer with over the years.
We've experienced a lot of technical issues with the computer. Making a computer system is very hard for this type of project. Also, our computer system has to have a lot of components, like a PID system for our servos, a gyro, a GPS tracking system, and getting all those to coordinate together on one circuit board can be complicated.
What are you doing to my line? What do you do?
All right, so how do you think this launch day is going to go?
Good. It's gonna go great. Excited.
Good to know.
I'm looking forward to it.
I think pretty good. The weather's pretty nice.
I'm excited. I want to see it go nice and straight.
Yeah, so we use the flow simulation add-in in SolidWorks, where we also design the fins, since it's a CAD software. And what we basically did is the original fin design had a lot of flow separation, which means that the trailing edge of the fin, a lot of that flow was diverting away, and so, which is not a great thing because the whole point of these active fins are to be able to redirect the flow. And so we wanted to redesign them by incorporating an iterative design process with the flow simulations and the flow simulation add-in in SolidWorks. To be fair, I think most of the issues are probably not going to come from the fin design. It's probably going to come from the code and from the PID.
I think what I enjoyed most was after the first AFS's rocket didn't deploy, we got the chance to redesign everything based on how we would redo it and make it better. So we basically got to go through on a system that we know works and tweak everything to make sure it works better and evolve it. And that was just cool to see.
5, 4, 3, 2, 1. Yeah! All right.
Because now we have a rocket that we all enjoy better, that works better, that's better functional, and we got experiences in building 2 different rockets.
I think this fin design, especially since it's like an airfoil design, it's going to do a good job. It's more so, the code and the PID, how how that was made is probably gonna be a big factor on how well they do, more so than just the design, but the fins can help out by being able to redirect more of that air.
I'm the avionics lead for our Active Fin Stabilization project.
So you write code for the team?
Yep. It's kind of a mix. I mean, it kind of depends on mood. Sometimes you're kind of burnt out from the day. The fun part is writing it. The not so fun part would be debugging it. This year, I feel like we've become more ambitious on what we've wanted to do, like especially for our liquid rocket engine project that we want to tackle. I feel like a lot more people have become more interested as we become more public. I was originally planning on just becoming a computer science major with maybe a concentration in software engineering. But because of RAM Rocketry, I've switched my major to computer engineering with a concentration in aerospace, which is a lot more difficult, but I'm very glad I switched over. I've learned so many new things that I would have just never learned if I stayed on the path I was going to choose. I mean, it's been kind of cool to like figure everything out on your own, but that's also kind of the consequence of not knowing if what you figured out is the right thing, or if your code looks good, or like if it's even working as intended. So the first launch actually was successful. So there was 2 launches that day. One was where the fins were static. We wanted to test the stability of the rocket. It went up, and at apogee, it deployed the parachute, although it was a little late. And then the second launch, we did do the active fin test, and it did work. It was a little iffy on ascent, but it was able to stabilize itself, but the ejection charge did not go off in time, and because of the way the rocket was designed, it was very top heavy, so it didn't eject in time, and it hit the ground at about like 60 meters per second. It was obliterated, like the flight computer was sticking through the nose cone. The only thing that was functional that we retrieved was the micro SD card where we logged all the data on.
What we're going to be moving into next year is we're trying to build some liquid rockets, a test stand, all that stuff. So all of that costs a lot more money than whatever this project was. I mean, we're looking at teams before, it was $12,000 just for the rocket. We also need to get a test stand. So fundraising wise, it's going to be a lot more. We don't get that much from the university. I mean, we'll get some, but to talk to the right people, talk to some companies, see what they do for us. But yeah, we're going to need probably around $20,000 to get these projects going. RAM funder, stuff like that to get it going. So yeah, I mean, we're going to use it to, study liquid rocketry. I mean, CSU used to have a very nice liquid rocket program. I think one of the first in the country to launch a liquid rocket at IREC. I mean, it's really cool. I mean, it's great for us. Looks great on resumes. It's going to help us in the future, when we're going into jobs. We already have experience with liquid rockets. It's going to really expand it. I don't know, it opens a lot of doors for us in the future, for sure.
So originally we were going to be more ambitious on what we wanted to do, but as we scaled it back to kind of more of the improved AFS design, there's still a lot we wanted to do. Better runtime of the program so it's not as slow, more sensors on it so the rocket knows where it's going, better PID, Kalman filter. There's a lot we needed to revise because the first flight, the code was almost too simple.
You mind telling me what happened with the AFS launch and why it's not happening?
So why it didn't happen last time is because the battery got overdrained. The buck converter didn't take the voltage output, so the circuit wasn't working, which this made the servo motors overheat. So we need to do some redesigning on them. So AFS will not be launching.
Have you ever had these kind of setbacks before on a project? And if they have happened, then how do you guys bounce back from it?
Well, I think it just kind of happens, and you have to just learn from it.
I mean, anything can go wrong. It's a very unique case. You're dealing with so many different things like weather. You have to deal with government policy. It's all probabilistic. I think I definitely want to go to space. I mean, I feel like that's any rocket scientist's dream, is to one day feel that weightlessness of anti-gravity. I'd like to see people end up on Mars one day. I think in my lifetime it's definitely possible, and I think we'll definitely learn a lot about life as we know it in the universe.
For me, it's almost like a stepping stone for what I want to do next in life, and that would be getting into the aerospace industry. Obviously, I can't guarantee anything. I'm not sure what my future path will hold, but I really hope it's involved with rockets because I really love rockets. They're very cool.
My biggest takeaway was personally to live and breathe every moment investing in a club that you care about, something that you have been developing over the past 3 years. And so I think just keeping at it, that's probably my biggest takeaway into everything else that I will do in my life. The club has been really helpful in terms of exposing me to this very diverse environment of so many different thinking personalities. This club has put me to the test of hard work, rigor, finding the best and robust solution to every problem we encounter as a team.